In this problem, we have an RC circuit. It's a single loop circuit with a switch as shown in the picture. The switch is closed at t equals 0 seconds. At some time later, we call that time t1, let's say, the voltage across the capacitor becomes equal to 11 volts. And the first thing we'd like to calculate is the current across the capacitor at that moment. Now, at the very beginning, when the switch is open, there's no current passing through the circuit, right? There's nothing going on. And then you close the circuit. Now that the circuit is closed, it's a closed loop, there's going to be a huge electric field in the circuit, right? The electrons are going to start traveling. How? Well, the electrons will leave the negative terminal of the battery and they will travel towards the right hand side plate of the capacitor, right? And then once they arrive at the plate, they will stay there. So there's going to be a negative charge building up on the right hand side plate. On the other hand, there's electric field everywhere in the circuit. Also on the left half of the circuit, there's the same electric field. So electrons will leave the left hand side plate of the capacitor and travel towards the positive terminal of the battery. So at the very beginning, there's going to be a large current passing through our circuit because our capacitor is neutral, and the electrons from the negative terminal of the battery want to go towards the capacitor, towards the right hand side plate, and the electrons on the left hand side plate, on the other hand, are attracted to the positive terminal of our battery. So then at the very first moment at t equals 0, we get the maximum current in the circuit. And at the very first moment, the capacitor acts like a wire. And for that reason, at the very first moment, the voltage across the terminals of the capacitor will be equal to 0. So the voltage across the capacitor is equal to 0, and the voltage across the resistor's terminals will be equal to the EMF voltage. But now the electrons are traveling towards the right hand side plate and out of the left hand side plate. Our capacitor is building up charge, it's accumulating charge, so its voltage will increase gradually. Well, why is the voltage across the capacitor's terminals is increasing? Well, because remember, voltage is proportional to the charge accumulated on the capacitor. V equals Q divided by C. And as Q increases with time, V will increase with time as well. So the two are proportional. Now, as the capacitor's voltage increases, the resistor's voltage will decrease. Remember, at the very beginning, the resistor had the same voltage as the EMF voltage. Now it will have less voltage because the resistor and the capacitor together are sharing the total EMF voltage. To see that, let's actually think about the voltage points in our circuit. Here I have also indicated with an arrow that our switch is closed. We have an operating circuit right now. Let's look at the voltage points A, B, and C. Our battery is in between voltage points A and C, so the voltage from A to C is 28 volts. Well, it's a drop, a decrease of voltage, of course. Or you can also go from A to C by passing through the lower branch. So you can go A to B first and then B to C. And again, you should end up with a potential difference of 28 volts, right? So then the EMF voltage at any given moment in the circuit is going to be equal to the voltage across the terminals of the capacitor plus the voltage across the terminals of the resistor. Let's express that idea with a formula. EMF equals V sub C, the voltage of the capacitor, plus V sub R, the voltage of the resistor. Now at time t1, we are told that the capacitor's voltage becomes equal to 11 volts. So we can use this information to calculate the resistor's voltage, and then we can use Ohm's law to calculate the current passing through the resistor at that moment. Let's also remember that the capacitor's voltage and the resistor's voltage change with time. Hence, I put T in parentheses to indicate that these are time-dependent values. But at any given time, the sum of those two voltages will be equal to the EMF voltage. Now in the next step I isolated V sub R, and then I'm also using Ohm's law to connect V sub R to the current passing through the resistor. So V sub R equals I times R. Again, I, the current passing through the circuit, is also a time dependent quantity. That's why I have the T in parentheses. Capital R, of course, is a constant value. It does not depend on time. Now let's go ahead and combine the two equations. I am going to set the right hand sides equal to one another and solve for the current. After combining the two equations and solving for I, we substitute the numerical values and we get I equals 0.13 amps. The next question is, when does the voltage across the capacitor become equal to 11 volts? So basically we want to calculate that time value T1. And in order to calculate it, we need to use the formula, the time-dependent formula for the capacitor's voltage. V as a function of T is equal to the EMF voltage times, in parentheses, 1 minus exponential of negative T divided by RC. Remember, R times C, that's the time constant of our circuit. Now we need to solve this equation for T, so let's rearrange our equation, isolate T, and then plug in the numerical values to calculate the value for T. So that will be our T1 basically. Here are the steps of the algebra. First, I divided both sides by the EMF. Then I rearranged my equation to isolate the exponential term. Once I have done that, I took the natural logarithm of both sides to get rid of the exponential, and I get negative T divided by RC equals ln of the term in parentheses. And next I rearrange my equation again to isolate T. Basically I multiply both sides by negative RC. After the numerical substitution, we get T equals 272 times 10 to negative 6 seconds, or 272 microseconds. Now let's calculate the rate at which energy is stored in the capacitor at the moment when its voltage becomes equal to 11 volts. Now that's really just the power of the capacitor at that moment, and power is equal to current times voltage. Let's plug in the values and calculate. Keeping two significant figures, we get 1.4 watts for the rate at which energy is stored in this capacitor.